4.1.5 Human activities. Human activities such as agriculture, it's mostly farming, but also animal husbandry, the raising of livestock, pigs and cows and stuff. Human activities such as agriculture, deforestation is cutting down trees, and urbanization, it's building cities, can alter stores and flows. Changes in land use, deforestation, and urbanization often lead to reduced evapotranspiration and increased runoff, leading to flash floods. That is, a flash flood is a fast, dangerous type of flooding. Agriculture. The type of agriculture being practiced can have varying impacts on drainage basin stores and flows. Arable crop farming removes vegetation cover during the harvest and so leaves the land vulnerable to erosion. Okay, so that's when if you plant a bunch of corn and then remove all of the, or wheat or something, wheat's probably a better example, and then remove all the wheat, there aren't any leaves left. There's nothing to stop the wind from blowing the soil away, which is erosion, causing erosion, or water from when the water is running down the surface from taking the soil with it. In contrast, pastoral, which is livestock farming. So arable farming was crop farming. Crops is plants. Okay. Pastoral farming, that's livestock or animals, may leave a grass cover throughout the year, but this may mean replacing a diverse forested surface with a grass monoculture. So that means just grass as far as you can see, the same kind of grass, leading to lower rates of interception, reduced storage, and decreased infiltration. Interception is determined by vegetation type, that's plant type, and density, how packed it is, how closely tight together things are growing. In farmland areas, cereals, that's like wheat, intercept less than broadleaf crops. Broadleaf, that means big leaves. Row crops means planting them all in a very careful row. Leave a lot of bare soil exposed between the rows. Infiltration is up to 5 times greater under forests compared with grasslands. This is because the plants and trees in the forest channel water back into the ground. Land use practices influence infiltration. You can look at table 4.3. Grazing, which is when the animals eat the grass, grazing leads to a decline in infiltration due to compaction of soil. It's because of if you have a lot of animals walking over a certain area, it packs down the soil, making it harder and firmer and more difficult for the water to seep through. Waterlogging and salinization are also common if there is poor drainage. Okay, so if there's not good channel, like not anywhere for the water to easily go into a channel or for it to go seep into the ground, okay, then you can get waterlogging, and salinization is the water becoming salty. Influence of ground cover on infiltration rates. Oh, that makes sense. Okay, so you got in the first column, you've got ground cover. What type of ground cover it is? Old permanent pasture. That's like old grasslands that are used to being having animals on them, grazing on them. Permanent pasture, moderately grazed. Permanent pasture, heavily grazed. Strip cropped, weeds or grain. Clean tilled, bare crusted ground. You can look up these different types of ground cover if you want to. And it shows how the infiltration rate varies with them. I think the main point of this table is to show you that what is growing on the ground affects how, or what's being done to the ground, how it's being used in agriculture affects how the water can go into the soil. Deforestation. As figure 4.7 shows, that is a picture, and that is on 343, page 343. So as figure 4.7 shows, the presence of vegetation increases interception, reduces overland flow, and increases evapotranspiration. Okay, so compare it to just bare soil or rock. When the vegetation cover is removed, for example in deforestation, you go in and cut down all the trees, the risk of more severe and more frequent flooding events increases. This is because deforestation reduces interception, increases overland flow, and reduces evapotranspiration. Deforestation is also a cause of increased flood runoff and a decrease in channel capacity due to an increase in deposition within the channel. Okay, so there's not all this good vegetation to stop and slow down the rain. Okay, so it just comes in torrents and runs through overland. The area experiencing deforestation is likely to be larger than the area experiencing urbanization. This is because deforestation may occur for land use changes, for example, the conversion to agriculture, so cutting down a forest to grow crops or have a pasture, industrial development, to build a factory, to make way for tourist developments, new resort, cutting down the jungle to build a resort, and to allow urbanization to occur. When you cut down a forest to build up a new part of the city. Hence, it is likely to have a more widespread impact on hydrological processes, including increased volume of sediment being transported by rivers. Okay, so deforestation increases the amount of dirt that gets suspended in the water and flushed away down the rivers. Increased overland flow leading to more frequent erosion, reduced interception, reduced infiltration, and reduced evapotranspiration. So figure 4.7 shows the influence of deforestation on drainage basin hydrology. Hydrology means the movement of water, and flooding. Okay, so you can look at those pictures. Take a minute to really understand what these pictures are showing. It's a good illustration of what we just read. And then there's a table 4.4 here. Changes in runoff and erosion following deforestation. Okay, so here's some good data showing that this is the case. Okay. Urbanization. Urbanization influences the hydrological cycle through the creation of highly impermeable surfaces. Impermeable, that means the water can't get through. Okay, such as roads, roofs, pavements, and smooth surfaces that are served with a dense network of drains, gutters, and underground sewers to increase drainage density. Table 4.5. That's right there below on the same page. Urbanization has a greater impact on processes in the lower part of a drainage basin than in the upper parts. Okay, remember the picture before that we saw of the drainage basin? This is because a greater number of urban areas are found in the lower, flatter parts of drainage basins than are found in higher altitude, steeper parts. Well, that makes sense, right? That's where we build cities, is in the lowlands, not up in the mountains so much. Urbanization can have conflicting impacts on hydrological processes, including increased erosion due to an increase in the volume of water getting into rivers, increased speed of flow and transport of materials in rivers due to enlarged channels, and less erosion due to riverbank protection schemes. Okay, so there can be less erosion because cities can have found different ways to protect the sides of the rivers, so that they don't erode away with the, especially if you have a winding river, then the erosion hits the sides, scoops it out, and that's why winding rivers kind of move. They don't stay in one place with time. They kind of snake around. Okay, but if you've enforced the sides with concrete so that it stays in a strip, well, you kind of you're stopping the erosion there because you're protecting the banks. It's the sides of the river. Okay, so in this table you have a column of urbanizing influence on one side, and then the other column is potential hydrological response. Okay, so it shows what on the left-hand column is something that happens due to urbanization, removal of trees and vegetation, and then what's the consequence? What could be the consequence? How could the water response change? So removal of trees and vegetation could lead to decreased evapotranspiration and interception and increased stream sedimentation. Initial construction of houses, streets, and culverts. So when you're building them, that can a potential response there can be decreased infiltration and lowered groundwater table, increased storm flows and decreased base flows during dry periods. Sedimentation continues while bare ground is still exposed. Okay, another urbanizing influence, complete development of residential, commercial, and industrial areas. Okay, so not the initial construction, but the complete development of it. Well, that can lead to decreased porosity, reducing time of runoff concentration, thereby increasing peak discharges, so that means the maximum amount of water flow, and compressing the time distribution of the flow. So big and fast. More flow and faster. Greatly increased volume of runoff and flood damage potential. So more likelihood of damage because you've got all these buildings there, right? Another urbanizing influence, construction of storm drains and channel improvements. Well, potential response is local relief from flooding, so there's somewhere for the water to go. Concentration of floodwaters may aggravate flood problems downstream. Okay, so you've got somewhere for the water to go, but what happens once the water gets there? 4.1.6 Steady state of water bodies. The steady state of any water body can be demonstrated using flow diagrams of inputs and outputs. These can be used to calculate sustainable rates of water harvesting from lakes, aquifers, and other water bodies. Okay, so how much water can we use? How much can we take over how long of a period in order for it to be sustainable? So that how much water can we take out of this river before the river dries up and we don't have a river anymore? Well, that wouldn't be very sustainable, right? So how much can we take out and the river still proceeds more or less as normal? The input of water into a drainage basin mostly occurs through precipitation, snowfall, rainfall, etc. However, there could be transfer from other drainage basins and from groundwater. Outputs include evaporation, transpiration, discharge out of the basin, and groundwater flow into other drainage basins. Figure 4.8 shows the world's water balance, while Figure 4.9 shows the water balance for the Amazon rainforest. Well, that's interesting. So we have Figure 4.8, the world's water balance. Precipitation hitting land is 26% of the total precipitation. Evaporation from land is 16% of total evaporation. And we've got transfer of water vapor, balance of evaporation, precipitation over oceans. So the water vapor moving from above the oceans to above the land. And then you have runoff, 10%, balance of precipitation, evaporation over land. Okay, so that's also those are the water moving water from the land to the oceans. Precipitation over the ocean, which again, 74% of the total precipitation. And evaporation, which is 84% of total evaporation, is from the ocean. That's what it's saying. That's where the clouds come from. Evaporated ocean water. And here we have figure 4.9, water balance for the Amazon rainforest. Okay. Yeah, we can look at that. That's interesting. As the flow diagrams represent long-term water stores rather than transfers, the moisture found in the soil and the bedrock may not be included. Okay. We have an example water balance here in the box. For water use to be considered sustainable, the volume of water used needs to be lower than the volume of precipitation left after losses due to evapotranspiration. Any use of groundwater also needs to not exceed the annual recharge. Okay, so the amount of water that goes into it, as this would lead to a decline in groundwater resources. That makes sense? You can't take out more than what gets put in. Unfortunately, in many areas, the use of water for farming has depleted water resources beyond natural recharge. That means you used it up. It's using it up. For example, the Ogallala Aquifer under the High Plains irrigates more than 20% of the USA's cropland. Okay, so they suck the water out, or they pump it out of the aquifer, which was, a rock with water in it. Okay, the aquifer is close to depletion in parts of Kansas because the water level has fallen so much. Okay, so the aquifer irrigates more than 20% of the USA's cropland. So they're taking more water out of the aquifer than what's being refilled into it naturally. Figure 4.10, impact of water use on the High Plains aquifer. Okay, so here is a graphic representation of what we just read. 4.1.7, water properties. Let's start over here with this little fact box. Specific heat capacity is the amount of heat energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Water has a higher specific heat capacity than land, i.e., it takes more heat energy to raise the temperature of water than of land. Okay, now we're going to read 4.1.7, water properties. Water, H2O, remember that's 2 hydrogens and an oxygen, is an inorganic compound formed from hydrogen, H2, and oxygen, O2. It can exist as a solid, liquid, or gas, and it covers over 70% of the Earth's surface as a liquid. In a water molecule, the nucleus of the oxygen atom draws electrons, which are negatively charged, away from the hydrogen nuclei, which are positively charged. Although the water molecule is electrically neutral overall, there is a partial negative charge on the oxygen atom and a partial positive charge on the hydrogen atoms. This arrangement makes water a polar molecule, bolded term. With water molecules, the partially positively charged hydrogen atoms of one molecule are attracted to the partially negatively charged oxygen atoms of nearby water molecules, causing attractive forces called hydrogen bonds. That's also bolded, hydrogen bonds. So hydrogen bonds are the attractive forces between water molecules. Water molecules stay close together, cohesion, that's what that's called, due to the hydrogen bonding between them. Hydrogen bonds are constantly breaking up and reforming. So So they're very loose. Cohesion is the force by which individual molecules of the same type attract and associate, stick together. Attraction between water molecules is due to hydrogen bonding. Land has a low specific heat capacity, which means that it heats up and cools down quickly. In contrast, water has a high specific heat capacity, which means that it takes a long time to heat up and cool down. This is because energy is needed to overcome the strong hydrogen bonds keeping the water molecules together. Hence, areas that are close to the sea have a more moderate climate, termed maritime. It's called a maritime climate when you're near the sea. Whereas those far from the sea have a more extreme climate, termed continental. Water has a very high surface tension, caused by the strength of the hydrogen bonding between water molecules. This allows some insects to walk on the water's surface. Many gases are soluble in water. CO2, carbon dioxide, is soluble in water, and increasingly oceans are becoming more acidic. Water also has high adhesion due to its polar nature. Okay, so water is a polar molecule. It's got the positive side and the negative side. Partially. Anyway. On clean glass, water may form a thin film because of the forces between the glass and the water molecules are greater than the cohesive forces between the water molecules themselves. Adhesion is the attraction between water and other substances, such as a surface. Do not confuse the terms cohesion and adhesion. Cohesion, co means together, is attraction between water molecules. Adhesion, ad means toward, is attraction to a surface. Water is also an excellent solvent, so many substances can dissolve in it. Substances that dissolve in water are termed hydrophilic, water-loving substances. An example of a hydrophilic substance is sodium chloride, that's salt, which dissolves in water, producing separate sodium cations, Na+, and chloride anions, Cl-, both surrounded by water molecules. Substances that do not mix well with water are termed hydrophobic, water-fearing or water-repulsing substances. An example of a hydrophobic substance is oil. 4.1.8 Oceans as carbon sinks. Over the longer term, carbon is taken up into living organisms as biomass that accumulates on the seabed. Seabed sediments contain inorganic carbonates and carbon compounds in organic matter that is not fully decomposed. Over millions of years, these sediments can become fossil fuels. Oceans are the largest carbon dioxide sink on Earth. Over geological time, more than 90% of the world's carbon has settled in the ocean. Biological processes, such as photosynthesis, convert the carbon from CO2, the gaseous stuff, into organic material, plants. Gradually, organic carbon settles into the deep ocean, or phytoplankton also. It's pretty rare, not just plants. The deep ocean has a higher concentration of carbon than the upper ocean. Thus, oceans have moderated the impact of increased atmospheric CO2, carbon dioxide, by storing vast quantities in seawater and deep sea sediments. If carbon on the ocean floor were lifted to the surface, the ocean would become a source of CO2 rather than a sink. Since the early 1800s, about half of the CO2 released through the burning of fossil fuels has been absorbed by oceans. Absorbed CO2 forms carbonic acid by dissolving into the water of the oceans. This raises the hydrogen ion concentration in the ocean, making it more acidic and limiting organisms' access to carbonate ions that are needed to form shells. Since 1900, the pH of surface seawater has fallen from 8.2 to 8.1 due to the quantity of CO2 absorbed by oceans. If the oceans continue to absorb CO2 at the same rate, by 2100, the pH of surface seawater could have dropped to 7.8, representing an increase in acidity of about 150%. That is not good for animals that need shells. During cold glacial phases, atmospheric CO2 levels may have decreased to around 180 parts per million by volume, and it is thought that much of this was stored in the oceans. By contrast, in the warm interglacial, CO2 would have been released from the oceans, and atmospheric CO2 levels may have been around 280 parts per million by volume. Current CO2 levels are around 400 parts per million by volume, indicating a substantial global warming. The long-term trend in the ocean carbon sink since the 1960s has been driven by the uptake of anthropogenic CO2. That means human-made CO2. About 25 to 30% was absorbed by the oceans. However, the ocean carbon sink varies by as much as 20%. Some scientists suggest that oceanic uptake of carbon could be reduced in future as a result of reduced emissions of CO2 due to climate change policies, reduced storage capacity due to increasing ocean acidification, and ocean warming leading to an increase in the volume of CO2 released from the oceans. 4.1.9 Carbon sequestration. There we go. Carbon sequestration. That is not an easy word, is it? Carbon sequestration and ocean acidification. Carbon sequestered in oceans. Sequestered, that means like kept in. So carbon kept in and away. Okay, so carbon kept out of the atmosphere. Carbon sequestered in oceans over the short term as dissolved CO2 causes ocean acidification. Okay, making the oceans more acidic. Over the long term, carbon is taken up into living organisms, and when the organisms die, the biomass, the bodies, the stuff from the dead organism, accumulates on the seabed. Seabed sediments contain inorganic carbonates and carbon compounds in organic matter that is not fully decomposed, so it isn't completely rotted yet. Over millions of years, these sediments can be compressed to become fossil fuels. So they just keep building on top of each other. Okay, so you got like layers and layers of decomposing dead bits of plants and animals. Okay, and then they get compressed under the weight of more and more layers. And that's how we get fossil fuels. The cause of ocean acidification is believed to be anthropogenic sources. Anthro meaning human, right? Anthropogenic sources, such as carbon emissions from industrial plants, power stations, cars, and planes. Figure 4.12 shows ocean acidification. You can take a minute to look at that. I recommend studying that figure a little bit. Point 1. Up to 1/2 of the CO2 released by burning fossil fuels over the past 200 years has been absorbed by the world's oceans. Point number 2. Absorbed CO2 in seawater forms carbonic acid, lowering the water's pH level and making it more acidic. Point 3. This raises the hydrogen concentration in the water, making the water more acidic, and limits organisms' access to carbonate ions, which are needed to form hard parts, like shells or corals. Approximately 30% of CO2 is absorbed by the oceans, where it turns to carbonic acid. Scientists estimate that oceans absorb around 1 million tons of CO2 every hour. Wow, 1 million tons every hour. Levels of ocean acidity vary globally. Increased acidity adversely affects levels of calcium carbonate, which forms the shells and skeletons of many sea creatures. This adversely affects coral reefs, shellfish beds, and fish stocks, causing slower growth and weaker skeletons, and disrupting reproductive activity. The growth rates of some coral species on the Great Barrier Reef, that's by Australia, have declined by 14% since 1990, either due to ocean acidification and/or to temperature stress. Early warning signs of increased ocean acidity include the decline of oyster and shellfish beds on the west coasts of the USA and Canada, disintegration of coral reefs in several regions. By 2050, over 90% of coral may be affected by local and global threats, such as global warming. A significant reduction in the number of pteropods, which are tiny shellfish that form the basis of food chains in high latitudes.